So what did we do in the review last time? Okay, so what did we do last time? Giovanna, you were there, right?
Yes, we did a classification of series. Then, yeah, we even say each.
Just a second. When you say classification of the series, you essentially are talking about what series? You're talking about the atomic spectra.
Yes, sir.
Atomic spectra. Remember this. See, there will be a lot of spectra that one talks about. I think most probably tomorrow we'll talk about the nuclear spectra as well, where it's the nucleus where essentially you have these energy levels and they are coming up and down. So a spectra is just a spectra. A spectra is just it's just different wavelengths of light that essentially are coming out of the atom or the nucleus, and hence being called atomic spectra or the nuclear spectra. So that is the essential classification we worked on. We classified things on the basis of the energy level that things are coming down to. So let's say it starts with some n energy level and it ends at n is equal to 1. Such a transition is called, what was it called? I forgot.
Layman series.
Timing series, then you have bracket series for n is equal to 2. It's called bracket, right? And you have blah 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 n is equal to 3, n is equal to 4, and so on and so forth. So yeah, that was the total distribution. We also talked about the energy of the, that was the class previous to that, but we talked about the energies of the levels and the velocities of the electrons around in the orbit, and hence other things. So yeah, we completed the whole chapter. Let's just do some questions to see if things are clear or not. Okay. Question. The shortest wavelength. The shortest wavelength of the bracket series. So one has to think about which is the shortest wavelength in the bracket series. In the bracket series of a hydrogen atom. Of a hydrogen atom, atomic number is given to be some Z, is the same as the shortest wavelength in the Balmer series. The series of the hydrogen atom. Find Z. So yeah, essentially the question says the shortest wavelength of the bracket series for hydrogen atom with the atomic number Z is the same as the shortest wavelength in the Balmer series of the hydrogen atom. So you have a nucleus, you have an atom with the atomic number Z, and you're seeing the shortest wavelength in the bracket series of that particular atom has the same wavelength as the shortest series in the Balmer of the hydrogen atom. So just equate the two and just calculate the value of Z from there. Go ahead. Excuse me. I'm sorry. Yeah, processing. Hello, Afroza. Lovely to see you. We're just doing some questions on the Bohr atomic model and atomic models in general. So yeah, this is the first question that I've written on the screen. So take your time. If you're not able to understand the question, just ask, okay? I'll repeat it. Okay, so any idea, Frota? Zubena? Any ideas?
So are we equating two of their wavelength?
Yes, essentially. Okay, so let's think about this for a bit. First of all, there's a difference in the question in the sense that here we're talking about an atom with atomic number Z and not hydrogen atom. So the number of protons in the nucleus is obviously greater. It is actually equal to Z. So what you have Z amount of let's say protons which are essentially in the nucleus, and there's this electron that's going around. This is the valence electron. This is the most outermost electron. Since this is hydrogen type atoms, so let's go back. So whenever you have such a problem, always go back to the start, which essentially means let's balance the forces. So what's the centripetal force that's acting on this electron? Well, it's mv squared by r. And what's the electromagnetic force that is acting on this? Well, that's K, which is 1 by 4 pi epsilon naught. Q1, Q2. Charge of the electron is Z, and charge of the number of protons is Z times E, because there are Z protons divided by R squared. So our derivation goes exactly the same way. So we just equate these two. From here, we get that Rn is equal to 1 by 4 pi epsilon naught Z times E squared by mv squared. So your radius for Z atomic number goes up by a factor of Z. This Z factor was not there when we were talking about hydrogen atom for obvious reasons, but now it's there. What did we do next? Well, we said that the orbits will be quantized. Quantized in what sense? Quantized in the sense that the angular momentum will be an integer multiple of h cross, right? What is the angular momentum of the electron? Well, that's just mvr. And saying that it's quantized, so it's n times h cross, where h cross is just h over 2 pi, right? From here, from these two equations, essentially, this is n. What we get? Okay, let's just do this calculation. This is like a 2-minute calculation. So you have v Yeah, I should just put it here. mv 1 by 4 pi epsilon naught ze squared by mp squared is equal to n times h cross. I'm just substituting this here. What we get, the v's cancel out, and you get. So I need to calculate v, right? So take this v on the other side. What does this mean? The m's also cancel out. That's brilliant. Yeah, 1 by 4 pi epsilon naught z times e squared by n h cross, not squared, by n h cross only. So this is the velocity that you have. Notice again, when you're calculating velocity for the z atom, it's just increasing z times, right? For the hydrogen, your z was equal to 1. That is all that was changing. If the solutions was exactly the same. So what you were getting here is for the hydrogen case, you get 0.529 n squared a naught, right? This you get as Rn when you take this p and substitute it back here and then calculate Rn. But if you have a z, how would that change? Will it be z times this or z squared times this? What will be the function? Any idea? Just substitute this back and see what happens. Just take this value here, v 1 by 4 pi epsilon naught z e squared by n h cross, and just put it in either this equation or this equation, whichever you think will be better. Either works. I would recommend just put it in here in terms of v here, and then calculate Rn and tell me what Rn is. We've done this calculation before. We're just calculating it. We've done this calculation for z is equal to 1. We're just calculating it for some general z. Any idea what you're getting?
Some doing.
Okay. Sure. Excuse me for a second. I'm sorry, not doing so well.
So we have to find the value of Rn, right?
Yes, absolutely.
So 4 pi epsilon into n square h square by z e square into m.
That is, yes. Yes, yes. So essentially, this thing that you're saying here. So all the z, the point where z will essentially come will be in the denominator, right? So essentially, Rn, what you'll get is 1 by 4 pi epsilon naught e squared by m, z e squared by m. This is from this equation here. It's 1 by 4 pi epsilon naught z e square by m and v square. You just substitute this value here, v square. You get a 1 by 4 pi epsilon naught z e square by n h cross square. Notice there's a whole square here. Notice there's a z square. Oh, sorry, this is not a z square. This is just a z. There's a z here and there's a z square in the denominator. So there will only be one z that will remain after they cancel out, and that will be the z in the denominator, right? So everything will be the same, other than there will be an extra z in the denominator. So Rn, what you will essentially get is 0.529 n square divided by z angstrom. It's important to remember where the z's come. Why is it important to remember? Because there might be a direct question. For example, a question like this, which is just which is telling you that the atom it has atomic number Z and it's not the hydrogen atom. So in order to calculate it directly, you need to remember where the Z's come. And actually, if you see it, it's not very difficult to figure out where Z's come. Where do the Z's come? The Z's always come in front of the E square. So any equation you have, search where the E square is, right? Look for the E square. So for example, this equation, there's an E square here, just put a Z in front of it. I put a Z in front of it here. Here, when you were calculating Rn, the E square was here in the denominator, right? And there's an E square in the numerator. So you had an E square in the numerator and an E square in the denominator, but there's a whole square here. So there's a whole square here. So it was 1 by E square. So hence the Z has to come in the denominator, and we see that the Z is coming in the denominator. So a way to figure out where the Z will come in directly just by seeing the equation is to figure out where E square is. Does that make sense? Does that make sense?
Yes, sir.
Are you sure? Because this is a trick that I don't think a lot of people know, but it works. It works everywhere. I've tried it.
So can you explain one more time?
See, if Z is equal to 1, that's just the hydrogen atom, right?
Yes, sir.
In this question, for example, you were given a hydrogen-like atom. This is a hydrogen-like atom, but with atomic number Z.
1.
But atomic number Z. This is not hydrogen.
Okay.
It has some atomic number Z, and that is exactly what you need to find out, right? You need to find out Z. So where will the Z come in will actually depend on where the E square is. That is all I'm saying. So for example, when we calculated 1 by lambda, in terms of the RH, when we actually doing this calculation, we figured out 1 by lambda is just RH times 1 by NF squared my 1 by NI squared, right? Now, there's no Z here. How do I know where the Z comes? Well, we can only figure out where the Z comes if we know what exactly Rn is. Rn, when we calculated it, was 2 pi square me to the power 4 divided by 4 pi epsilon naught whole squared h cubed c. This was the value of RH, correct? If you go back to your calculations, you'll see that this is the value of RH that we got. Okay, there was an h cross cube here, but 2 pi इसको मैंने इधर उधर कर दिया, so that's why it's figured out. Now, if I want to put a Z here, we'll calculate how many E squares are there. Well, there are 2 E squares here. There's an E square multiplied by E square, right? So there will be a Z square in the numerator here. So 1 by lambda is just Z square RH 1 by NF squared minus 1 by NI squared. Does this make sense? This is for Z is equal to 1. This is for some general Z.
Okay, sir. Got it.
So put the Z wherever you see an E square. E square, just put a Z there. That's how you know that is general. Okay, so now coming back to the question, we still not reached the question. We're still discussing the prerequisites to the question. The question said the smallest wavelength of the bracket series. So bracket series is which one? Bracket series is when it comes down to NF is equal to 4. Yes. NF is equal to 4. This is bracket series. And this should be equal to the Balmer series, right? That was the question. Yes, no, maybe.
Yeah, it's same as both are same.
Both won't be the same, right? So essentially, so let's see how this works. So smallest wavelength means the largest energy gap. What will be the largest energy gap? The largest energy gap will be when the electron is coming from infinity to whatever n you want. So in the bracket, it's coming from infinity to n is equal to 4. In Balmer, it's coming from n is equal to infinity to n is equal to 2. That's the highest energy gap that anyone can cover, right? So hence the lowest wavelength. Okay, so in both cases, my initial Ni is equal to infinity. So in both cases, this 1 by Ni square will just go to 0. Lovely. So let's take in the first case what happens. It's saying that Z square RH multiplied by NF square. NF is the final, so 1 by 4 squared minus 1 by infinity squared. So this is just 0. Should be equal to RH multiplied by 1 by the Palmer series, 1 by 2 squared minus 1 by infinity squared, which again is just 0. So now you have the RH cancels out. So you have Z as the only variable in this whole equation. All of the other things are constant. So you can just calculate the Z. So you have Z squared times 1 by 4 squared should be equal to 1 by 2 squared. So 1 by 2 squared, well, this is just 1 by 4. And this 1 by 4 cancels out with one of the 4's here. So my Z square turns out to be 4. This implies Z is just 2. It cannot be minus 2 because Z is always positive. So you only take the positive solution of this equation. So Z is equal to. Does that make sense?
Yes, sir.
Pakka? Absolutely. No doubts here?
So for first case, Z square RH, right hand side of that equation, it's like RH into 1 by 2 square, right?
Yes.
Okay, so clear.
Why is that the case? Because that's the Palmer one, right?
Okay.
It comes down to N is equal to. Okay, lovely. Good question. Good start. We discussed something new also, talking about Z and where. So remember this because there are a lot of questions which involve Z, especially from this topic. So remember where Z comes. Z only comes wherever you have an E square. Make sense?
Yes, sir.
Okay. Okay. This is a nice question. You think about combinatorics. Okay. So in a hydrogen atom, what you have is the electron is in the nth excited state. So it's in the nth state. The ground, you have the ground state, which is the first state, and the rest of them are just the excited state. You have the first excited state, which is n is equal to, second excited state, n is equal to 3, third excited state, n is equal to 4, and so on and so forth. So nth excited state would be n plus 1th orbit. And it's excited state. Then what happens? It comes down to the first excited state, to the first excited state by emitting 10 different is the keyword wavelengths. What is the value of n? How do you proceed with such a question? Think about this. Take like 2 minutes. Ponder upon it because this is a slightly tricky question. One needs to think about how these. You need to draw the energy level diagram. Just to try to draw it and see if you are coming from, let's say, the third excited state to the first excited state, how many different ways can you come there? Then you try the fourth excited state, then you try the fifth excited state. And at some point, you'll see that there will be 10 different ways to come down. That will be your value of n. That's how you progress.
So is it 11?
No, I don't think so. But can you tell me what's your process of thinking about this?
From nth to first state, it'll be like n minus 1, right?
Just so essentially, let's just think about this. So you have the ground state, which is the lowest energy state. Then you have the first excited state, you have the second excited state, and dot 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 dot. So you have the nth excited state. Now it's saying that it comes down to the first excited state, right? So this is where it finally ends up. And they're also saying that there are 10 different wavelengths that come out. If there are 10 different wavelengths, what does that mean? That means that there are 10 different transitions. So 10 different wavelengths mean that there is 10 different transitions, right? Does that make sense? Why it should be the case?
Yes, sir. Got it.
Lovely. So let's say you're coming down from the second excited state to the first excited state. Well, there's only one way to do that, is that you just come down. Right? There's no other way to do that. So only one particular wave will come out. Now let's say you're working from the third excited state. So this third excited state, well, there is one way to come down, which is one down and then here. So you'll have two different wavelengths here, or you can directly come down. So you have three different wavelengths here. Okay, that seems promising. So when you have come from 2 to 1, there's only one way to do it. When you come from 3 to 1, there are three ways of doing it. Well, when you come from 4 to 1, how many ways of doing it are there? Well, there is one way is to come down to the third one, then come down to the second one, then come down to the first one. That's one way of doing it. Other way would be come down to the second one and then come down to the first one, or come down to the first one and then come down to the second one, or come down directly. These are the only ways to do it, right? How many total ways are there? 1, 2, 3. Sorry. How many different wavelengths that are coming out here are 1, 2, 3, 4, 5, 6, 7, 8. There are only 8 wavelengths that are coming down from 4 to 1. That seems promising. We need 10 different wavelengths. Okay, so let's then try n is equal to 5. This was n is equal to 4, right? Let's try n is equal to 5. Well, n is equal to 5 coming down to n is equal to 1. Is there a pattern here? Is there a formula that you can make out of this? Of these combinatorics? Because essentially what you're doing is combinatorics, right? It's like if you go back to your maths chapter on permutations and combinations, it's something like that, because these are essentially different ways of arranging how these things are coming up. So essentially it's just still NCM type of a question, right? You're choosing for example, you're choosing 3 ways to come down out of the total number of ways to come down. So it's still a similar problem. So you can think of this question in terms of permutations and combinations, and I would encourage you to do that. But right now, let's see what happens when n is equal to 5. You have 1, 2, 3, and 4 ways. So 4 different wavelengths that are coming down here. Other than that, you can come down here and here, or you can come down here, here, and here. You can come down here, here, and here. And so there will be many ways. But still, there won't be 10 different transitions. 10 different transitions will only come when you're actually working with n is equal to 6. So when you're going from n is equal to 6 to n is equal to 1, you'll have 5 different wavelengths that are coming, because just 6 to 1. So it's 1, 2, 3, 4, 5 different here. Then you have the total one, 6 different. Then you have only one from here, because this is already is added. So you have 1, 2, 3, 4, 5, 6, 7. Then you have 8, 9, and 10. 8, 9, and 10 will be this one. Yes. So that's why you'll have 10 different ways of doing the transition. So it's just drawing the thing and just adding them up. Does this make sense?
Yes, sir.
Should I repeat this if it
Yes,
doesn't
sir.
make sense? Huh?
Clear.
Yeah, lovely. Okay. Let's move on to the next question. This is Also an interesting something that will make you think. A neutron. So you have a neutron which is moving at a speed v. Let's call it v, and it makes a neutron moving at speed v collides head on with a hydrogen atom. Hydrogen atom which is in its ground state. So the atom is in its ground state, and you have a neutron that's literally just flying towards. Okay, apologies, my internet just went off. Are you there, Jabana? Hello. Hello, Froza. Hello, Froza. Apologies, my internet just went off. Jabana is also here. Lovely. Sorry.
Sorry, sir. It just went like connection went away.
Yeah. Even my mind just decided to be like, I'm going Tata by that. Anyway, let's just continue from where we were. We were writing this question down. Obviously, it's all gone. So I have to write it again. A neutron, which is moving at a speed v, collides head-on collides head-on with a hydrogen atom. Collides head-on with a hydrogen atom, which is in its ground state. So you know what the state of the hydrogen atom is. What you need to find out is find the minimum kinetic energy. The minimum kinetic energy of the neutron for which complete or partial inelastic collision may take place. So remember what elastic and inelastic collisions mean?
Yes, sir.
We talk about when there is no energy loss, and inelastic collisions are when there are energy losses. So where will the energy be lost in such a situation when you have a neutron that essentially comes in and there's an electron that goes around and it just head on just collides with this atom? Where will the energy go? If the energy is supposed to dissipate, where will it go? And the only place that it can go is that the electron absorbs that energy and then goes to a higher energy state, and hence that collision will be inelastic because there will be some loss of energy and all the total energy will not be conserved. So hence it won't be an elastic collision. So the question is, what is the minimum kinetic energy that the neutrons would have so that the collision between this neutron and the hydrogen atom, which is in the ground state, will be inelastic. Okay, go ahead. If there's any doubt in this question, just ask, please.
So complete or partial in electric collision, right?
Not inelastic, inelastic.
Okay, sir.
So you have elastic collisions and inelastic collisions, right? Let's write this down again because it should be clear. Given the mass of neutron will be equal to the mass of the hydrogen atom, which is equal to m over 1.67 into 10 to the power minus 27 kilograms. I just always found it funny when people measure the weight of neutrons and atoms in kilograms. What's the bloody point? Okay, any ideas? How do we proceed here? Any thoughts?
Not yet, sir.
Okay. Whenever you have a question like this, let's see how we essentially go about doing such a question, because this is a very typical question that you might see in some of these entrances, and the way we're going to solve it is also quite typical of things. And there's one key point that I want you to take away from this question, which we'll see in some time. So initially, let's think about what is happening initially and finally. Why are we doing, and how do we know we have to do this? Whenever there's a collision that is taking place, there are two things that can happen. One, it is an elastic collision. Two, it is an inelastic collision. Obviously, if it's an elastic collision, what does it mean? It means energy will be conserved. So for an elastic collision, you will have energy conservation and momentum conservation. For inelastic collision, you'll only have momentum conservation. So this is inelastic collision. You will only have momentum conservation until unless you can figure out exactly whether how the energy is being not conserved. In the sense that when one says that energy is not being conserved in inelastic collision, that means that energy is being used in terms of heat, in terms of, for example, in this case, exciting the electron. But if you can somehow quantify how much that energy is, for example, in this case, that you can, because delta E will just be the energy from going to the ground state to, let's say, the first state or the second state. It will be fixed energy levels, right? These are energy levels that you will know. So that's why the energy that's lost in the inelastic collision, you know exactly how much it's lost. So what you can do is let's see what is happening initially. What you have the speed of the neutron to be v. You are given this to be v, some v, and initially your v is equal to 0, right? Let's call these two vi because of I for initial, and finally let's say that actually we need different things for this, right? Yeah, okay. Let's not call this v. Let's call this u because initial. So you have u of the neutron and u for the atom. Let's call it UH for hydrogen. This is 0 and this is some u. And you have v for neutron for the final velocity of the neutron, and you have, let's say, the atom goes in this direction. You have some final velocity of the hydrogen atom. So h. Oh, this n and h will look exactly the same, so it will be confusing. Be careful. Okay, so essentially what is happening, the collision between the hydrogen atom and the neutron will be inelastic, as it is given in the question, and that means that this implies that some part of the kinetic energy of the neutron will be used to excite the electron to a higher energy orbit. Does this make sense?
Yes, sir.
Lovely. Okay, so if this makes sense, then let's continue. So with momentum conservation, what do you have? You have mu, where u is this, is equal to your m. Since the masses are the same, we just consider this mass to be m, both of them. You have mv for the neutron plus mv for the hydrogen. Right? This is momentum conservation. What about energy conservation? As I said, that energy will not be conserved, but if you know where the energy is going, then it is conserved, because energy is always conserved, no matter what. So what does energy conservation says? It says that the kinetic energy initially, so which is m half m u square, that's the only energy that the system has initially, should be equal to half m v for the neutron square, so final neutron velocity, final neutron kinetic energy, and final atom kinetic energy as well, which is half m vh square, plus some delta E. What is this delta E? This delta E is essentially the energy difference between let's say the first and the second order. excited orbit, or the ground state at the first excited orbit. So it can be any of these things. Lovely. Let's clear this all and let's write the equations down again. We have mu is equal to mbn plus mbh. You have energy conservation, so you have half mu squared is equal to half mbn squared plus half vh squared plus delta E. Now let's simplify this. Let's divide the whole thing by m by 2. So that let's just remove all these m by 2s here. What do you have? You have u squared is equal to vn squared plus vh squared plus you'll have a 2 delta E by m, right? So dividing the whole thing by m and multiplying the whole thing by 2. Does this make sense?
Yes, sir. Can you take last page? Last slide.
I'll have to undo. Just give me a second. I'll just do it. That's a lot of undos. Yeah, apologies. I should ask before moving ahead. Yes, we're back here. Let me know when I can move on.
So is it mu equal to mvn plus nvh?
Yes. So momentum conservation, right? So this is the initial momentum, and this total is the final momentum, right? Because initially the neutron was only moving with u, the hydrogen was stationary, so UH is equal to 0, and finally we are saying it is moving with some Bn, then the neutron and the hydrogen is moving with some BH.
Okay, done, sir.
Lovely. Okay, let's write these things down again. You have mq. This is because momentum conservation is equal to m Vn plus mvh, and energy conservation give us half mq squared should be equal to half mvn squared plus half mvh squared. Okay, this is n and this is h. I need to be very careful about this. Plus delta E, and as I said, let's just divide the whole thing by m and multiply the whole thing by 2. What do you get? You get u squared is equal to vn squared plus vh squared plus 2 delta E by m. Okay, how many equations and how many variables are there? Let's write down the variables. Vn is a variable. Vn is something that we don't know, and so is vh, right?
Yes,
These are the two things that we don't know. Delta E is just the energy difference between the orbits, so we know that we can figure that out. M, mass of the neutron or the atom, we know that. Everything else we know. So the only variables are just Vn and Vh. How many equations you have? Well, you have one equation here and the second equation here. You have two equations and two variables. We can be happy and solve these two together. How do you solve these two together? Well, simplify this first. Let's cancel the m's out, the first equation, and we need to substitute either Vn or Vh, whichever you like. I don't like Vh so much, so I'll remove Vh. So my Vh is equal to u minus Vn, right? So I'll take this value of Vh and I'll substitute here. And what do I get? You get u square is equal to Vn square plus u minus Vn whole squared plus 2 delta E over m. Make sense? Let's simplify this further. What do you get? You get u square is equal to Vn square plus u square, let's open this bracket, plus Vn square minus 2u times Vn. So you opened up the whole thing, is equal plus 2 delta E over M. Notice the u's cancel out because it's the same u on both sides of the equation. Your Vn square plus Vn square will just make a 2 Vn square, and you'll have a 2 which is common. So let's just write this down here. What you do get, why is this not going away? Okay, now you're gone. What do you have? You have 0 is equal to 2 times Vn square minus 2 times u times Vn plus 2 delta E phi. So let's cancel the 2's, and you have Vn square minus u times Vn plus delta E over M is equal to 0. Is this clear till now?
Yes, sir.
Lovely. Now what you have is one variable, one equation, and this equation is a quadratic equation. We know how to solve quadratic equations, right? Vn, the value, if Vn square minus u Vn plus delta E by M is equal to 0, it's a quadratic equation. Let's find out Vn. Vn is just minus V plus minus square root of B square minus 4AC upon twice of A, right? Where if this is A, B, and C. So what's the value of B? B is minus u. So you have u plus minus square root of B square. So that's u square minus 4A. A is just 1. So that's just 1. That's lovely. Times C, that's delta E over M over twice of A. A is just 1. So you have 2 here. Now notice that your Vn has to be real, right? Your Vn cannot be imaginary. It cannot be an imaginary number, right? It has to be a real number. And for this to be a real number, whatever is there inside the square root has to be positive, correct? Yes, no, maybe?
Yes, sir.
So if this has to be positive, this means that u square minus 4 times delta E over M has to be greater than 0, greater than equal to 0, if this has to be true. Yes? So let's simplify this a bit. What do you have? You have, let's take this M upstairs. So you have mu square over 2. This is the initial kinetic energy. So I took a 2 from here, or the 2 here is remaining, and I took the M here and placed it here. Should be greater than equal to 2 times delta E, right? And the minimum delta E. So what the question was essentially, what is the minimum kinetic energy, right? What is the minimum kinetic energy for the neutron for which the collision is inelastic? So this is the kinetic energy. So let's just write this as kinetic energy. This should be greater than equal to 2 delta E, right? So what is the minimum value of kinetic energy? It's 2 delta E. So can I rub some of this?
Yes, sir. Left side.
Okay. This. So your kinetic energy is just greater than equal to 2 delta E. So the minimum value of kinetic energy is 2 times delta E. This is the minimum value. This is the minimum value. And 2 delta E. What is delta E? Delta E, the smallest delta E that we have is, since the atom is in the ground state, so it's the first state. And since it's the hydrogen atom, what is the energy of the ground state? Well, we already know it's minus 13.6 electron volts. What's the energy of the first state? It is minus 13.6 divided by 2 square divided by 4, so which is minus 3.4 approximately electron volt. So the energy difference is 10.2 electron volt delta E. This is the smallest energy difference. Let's just put it here. You get 2 into 10.2 electron volts, which is equal to 20.4 electron volts. So 20.4 electron volt is the minimum amount of kinetic energy that the neutron should have in order for any head-on collision with a hydrogen atom in the ground state to be inelastic. Does this make sense?
Yes, sir. So in right hand side, Yeah, Vn equal to u plus or minus root of
Yeah.
4 square minus 4 into 1 delta
Not
e.
4 square. This is u square.
Okay, sir.
See, it's essentially using the fact that ax square plus bx plus c is equal to 0. If you have this equation, which is the quadratic equation, the solution of this is just x is equal to minus b plus minus square root of b square minus 4ac by 2a, right? This is high school mathematics, right?
Yes, sir.
So essentially just use that fact. I hope that's clear. So it's in to your answer. I'm sorry?
Clear, sir.
Lovely. Is it okay if I move on to the next question?
Okay, sir.
Okay. So I mean, my essentially question was all of this is done, right? You've written all of this down. Okay, lovely. Okay, I'm clearing this. Slightly tricky question, but it will you'll remember things in your head slightly clearly, hopefully. The wavelengths of the K alpha. You remember the K alpha and K beta lines? We did talk about this, right?
Yes, sir, we did.
X-rays. So K alpha and K beta, we're saying they're X-rays. Are essentially you're given the wavelengths, so you're given the wavelengths to be 21.3 picometers. Picometers is 10 to the power minus 12. Remember that. You have billion as 10 to the power minus 9, and pico, sorry, 10 to the power 9. And pico is 10 to the power minus 12 essentially. So this is 21.3 into 10 to the power minus 12. Yeah, sorry. And the other one is given to be 18.5 picometer respectively. Find the wavelength of the L alpha X. Find the wavelength of the L alpha. L alpha line of the material. KLMN. Go ahead. If you draw the energy level diagrams, you will realize that things are actually quite simple.
Sir, find the wavelength of the
L alpha line. K alpha and K beta are given to you, and you need to find L alpha. You need to remember what these lines were essentially. So K alpha is used for which lines? Do you remember?
Layman.
Line, yes. And L alpha? See, it's KLMN, right? So L has to be Balmer. It's Lyman Balmer Bastian bracket. So KLMN. I think I wrote H in the notes. Sometimes they use H, sometimes they use L. But here they mean Balmer for L. Okay, thoughts. Let's see. Let's see what's happening to the energy level diagrams. K alpha and K beta are essentially your Lyman series. Lyman series essentially says that you're going from n is equal to, let's say, 2 to n is equal to 1 and n is equal to 3 to n is equal to 1. So you're coming down to n is equal to 1 essentially. The first line is called K alpha. So n is equal to 2 to n is equal to 1. So it's n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 2 to n is equal to 1 transition. This line will be K alpha line, correct? And n is equal to 3 to n is equal to 1 transition. This line will be equal to, this will be the K beta transition, correct? What about the Balmer? The Balmer series, you're coming down to n is equal to 2, and the alpha line will be the first line, so n is equal to 3 to n is equal to 2 will be the L alpha line, right? So essentially this line, right? Make sense?
Yes, sir.
Okay, now from the diagram, if you look at the diagram, can we do that?
Sir, can you repeat it?
Yes. So I'm saying that the energy difference between n is equal to 3 to n is equal to 1. So delta E, n is equal to 3 to n is equal to 1 is equal to, so this whole difference is equal to this difference plus this difference. So this difference being n is equal to 3 to n is equal to 2 is equal to delta E, n is equal to 3 to n is equal to 2 plus delta E from n is equal to 2 to n is equal to 1. So this whole thing is equal to this plus this. Yes, no, maybe?
Yes, sir.
Because these are just energy levels, right? So the total energy has to be equal to the sum of the energies by definition.
Okay, sir.
Okay, so what was delta E? Now, we know how the energies are essentially related to each other. Delta E is just proportional to 1 by lambda, right? Yes, no, maybe?
Yes, sir.
Why is it proportional to lambda? Because E is equal to h du or hc by lambda. So it's inversely proportional to lambda. So that's why, and hc are both constant. So let's just replace these by 1 by lambdas. So you have 1 by lambda from the transition 3 to 1 should be equal to 1 by lambda from the transition 3 to 2 plus 1 by lambda for the transition 2 to 1. Now, lambda for the transition K alpha is given. K alpha would be this one from 2 to 1. So this is given. And the other one K beta, which is from 3 to 1, which is essentially this one, is also given. So let's just put in the values. K alpha, and you need to find 1 by lambda 3 to 2 plus this is given to be 1 by 21.3 pico, so 10 to the power minus 19, and 1 by no, minus 9 minus 12 meters, and you have 18.5 in 10 to the power minus 12 meters. So let's do this calculation. Let's see what happens. You get 1 by lambda 3 to 2, which is essentially what you need to find out. is equal to 1 by 21.3. I just take 10 to the power 12 here. 20.3, 1 by 18.5. Oh, I actually wrote it down the other way around. Nice. It's not. So since this is this, you have 1 by 18.5 divided by 1 by 21.3. Please do this calculation and tell me what lambda 322 is. It should essentially turn out to be around 140 picometers from this calculation here. Can you do this calculation and just verify if this is the right answer or not?
Okay, sir.
Does the answer make sense, Rubena?
I'm getting like 10 raised to 12 by, no, not 10 raised to 14 by 710.
That's just put it in a calculator, no? Just use a calculator to do this. I mean, 1 by 18.5 minus 1 by 21.3. It's actually difficult to do. Just use a calculator. Calculators are your best friend. I always carry a calculator with me.
So for the right hand side, like 1 by 18.5 minus 1 by 21.3, I'm getting 0.00710. Like it's
Yes,
a huge
yes,
number.
yes, yes. And then you'll have to invert it also, no? Because this is in the denominator, so you'll have to invert the whole thing.
Done, sir.
You're getting 140,
No, I'm not getting exactly that.
but it's close by.
Yeah.
That is fine. If it's close enough, then it's good. Just a second. Yeah. Not finding any good questions anymore. Okay, yes, let's just do this. This is a decent exercise to do. Okay, let me show you some. Let me just draw some energy levels here. We have one, 2, 3, you have 4, and you have 5. Okay, so these are the energy levels of, let's say, of any random random atom that you're talking about. Obviously, the distance is essentially proportional to the energy gap between these different n is equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, n is equal to 5 orbits, right? And you can just keep on going on to n is equal to infinity. My question is as follows. Let's say you have a transition from n is equal to 3 to n is equal to 2. Let's call this transition A. Then you have another transition which is from n is equal to 4 to n is equal to 2. Let's call that transition B. You have another transition C, which is from n is equal to 4 to n is equal to 3. And you have another transition, this one D, which is n equal to 5 to n is equal to 4. My question is, which will have the highest wavelength out of A, B, C, D, which will have the highest energy, which will have the highest angular momentum. When I say highest angular momentum, I mean which state will have highest angular momentum. Will it be the n is equal to 1 state, n is equal to 2 state, n is equal to 3 state, n is equal to 4 state, n is equal to 5 state? Obviously, there's no angular momentum when talking about transitions, right? So for transitions, I just want these two, which will be the highest lambda and the highest energy. A, B, C, D. Just tell me the energies. You can kind of find out the lambdas from there. Am I audible? Yes.
Yes, sir.
So, which will have the highest energy? A, B, C, or D?
I guess D will have highest.
D will have the highest energy.
Yeah.
See, when it's transitioning, right? It's the electron is transitioning from, let's say, n is equal to 4 to n is equal to 2. The energy gap. This is the energy gap here. When it's transitioning from n is equal to 5 to n is equal to 4, this is the energy gap only, right? Obviously, this is so small. This is so big, right?
Yes, sir.
So that's why the energy delta E in the B process will be the highest. Then you will have A, delta E A. Then you will have C, delta E C, and then you will have delta E D. This will be the energy difference. It's the energy gap. It's the difference in energy that's important. Make sense?
Yes, sir.
If you have energies in this relation, you can find out the relations of lambda from exactly this thing. How? By realizing that delta E is proportional to 1 by lambda. So if I want to make a lambda arrangement, just reverse the signs. This means that lambda in B will be the smallest, lambda in A will be the next, lambda in C will be the next, and lambda in D will be the largest. So yes, the wavelength that is coming out because of this transition, D, the smallest transition, will be the highest. But that means that the energy will be the lowest.
Okay, sir. Understood.
Okay, let's stop here. Next class, I am going to finish your modern physics, most hopefully tomorrow. Then I complete the nucleus part of the syllabus, and I think we'll be done after that. We'll do more questions, obviously, as we come along. But that's it for today. Thank you for listening.